Let us continue with the topic, and our next result will be theorem. Let E be a Banach space such that E dual is separable then E is also separable. Very good. Very good. So, let's start the proof. Under the assumption E star is separable, so assume that we have here Fn is a sequence contained in E star is dense in E star. Very good. So, by using the definition of supremum, for every n belonging to n, we can find the existent element xn belonging to E, satisfying that this xn is equal to 1, and we have here the norm of Fn, and we have here that Fn on Xn is larger or equal to 1/2 the norm of Fn. Indeed, just explain it. Indeed, we have here the norm of Fn, and assume that Fn is not equal to 0, right? Then this will be equal by the, we can write it now, supremum, and we can also add it exactly equals to 1, and we can put here Fn on X. So we can just simply say for every epsilon, then we can take this epsilon to be 1/2. So by taking epsilon equals 1/2 Fn, there exists an element xn in E. Of course, it's one of those. Here we have the condition, so that means your xn must be equal to 1, satisfying the property, satisfying that this is the supremum, so that means satisfying the property that Fn minus this epsilon, so this means 1/2 Fn, so that means minus this epsilon, this is your epsilon, is going to be smaller than, let's see, smaller than that value Fn on Xn And that's exactly what we got. This is 1/2. And that one is Fn. So very good. So you have the set. You have the set Xn. But now this is something that is not yet to be the dense set. In order to get the dense set, we'll put it like this. I say S, then put, maybe I'm less, 10, put, and I have here the set S to be, and I say span again. Span, that means linear combination, but with the rational coefficients. So of this generated by this sequence Xn. Finite linear combination. So since the countable union of countable sets is countable, so you get immediately that 10. So S is countable. We will show that S is dense. S is dense in E. First, notice that S is definitely dense in the subspace. Call this subspace L, which will be equal to span, but this time I take the real coefficient. So that's a linear subspace. So, in order to conclude the proof, we need to show that L closure is equal to E. 10 means L is also dense, so it's enough to show that the S is dense in E. And how to prove it? So suppose F belongs to the L perpendicular. So, if F belongs to the perpendicular, we need to show, particularly we need to show that F is identically 0. That's what we need to show. Okay, so what do I know? Since, again, since the sequence Fn is dense in E star, for every for every arbitrary epsilon larger than 0, we can say like this: there exists an n belonging to such that the norm of F minus Fn is smaller than, let's say, put here epsilon. So what do we have here? Then I have here that 1/2, then maybe, of course, then we have, and this will be 1/2, and I take exactly this Fn, that one is smaller equal, and then I have here Fn, this is Xn, and that one, of course, what do I have here? So since F, put it here, so that means F is orthogonal to L, so that implies that F on Xn, because Xn is in L, is equal to 0. So I can rewrite this down, this expression, write it down. This is the same as Fn minus F, and this will be Xn minus Xn. But that one is next, of course, smaller equal. And we can write it now, supremum of X, let's say, smaller equal than 1, and that will be Fn minus Fxn, and this is nothing else than the then this is the norm of Fn minus F, and that is smaller than epsilon. That's what it is. That was our assumption. So we can now continue. For any x, for this arbitrary epsilon. So remember, this is still arbitrary epsilon. So this is an arbitrary epsilon. We have here that the norm of F, and this can be written like this. This is the norm of F minus Fn, and plus, and this one is the norm of Fn. Very good. But what do I get here? From the previous line, I'm getting here that this one is smaller than, you see, here and here, than 2 epsilon, and that one we chose in such that was smaller than epsilon. We are getting it is smaller than 3 epsilon, and the conclusion follows. The conclusion follows. That means simply that the norm of F must be equal 0, because epsilon was chosen arbitrarily. That's it. So we have here the first result of the session. So let's do an example. So let me do example, and maybe call it like a remark is better. Remark. Notice that the converse statement of the theorem is not true in general. So indeed, consider the space E to be, let's say, L1, 10, of course, as one of our assignments shows, L infinity will be the dual, and one can easily verify that L1 is separable. Let me point out why. Here we can take as the dense, so I simply say span again over Q, and we call it this one the basic vectors, like this, basic vectors in L1. So what is En? En is the vector like this one. Sorry. 0, 0, blah, 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 1, and then we have 0, 0, all the zeros follow. So this 0 here stands, sorry, this one stands on the end place, so this was the end. So you can see that this is this dense set, this set is dense in L1. On the other hand, we can define the set, and let's call this set D. Why not D? For the space Ln, so I'll put it like this. This is the set of all vectors like this x n, and this will be this vector, maybe not x n, such that x n is belongs to the set either 0 or 1. So that means this is the set of all sequences such that x is equal to x1, x2, and xn, and goes on. So each of those numbers is either 0 or 1. So for example, 0, 1, 1, 1, 1, 1, 1. It's one example. 0, 0, 1, 0, 1, 0, 0, 0. So of course, if you look at this set, you can think about it as the infinite sequences, and this it brings you on your mind that if you have here any real number r belonging to the interval 0, 1, this number can be represented as in a unique actually way by this sequence. Yes, by this sequence. Maybe not necessarily unique. Yes, it's not. So I put it like this: x1, x2, xn, and so on. It's not never necessarily. There may be, let's say, repeating fractions, of course, but it doesn't. It tells you simply that this sequence, let's say, by using these representations, you can basically create a map. So put it like this: phi that goes from the set of D, and this is to the interval 0, 1, namely phi of the sequence x will be exactly equal 0, x1 digit, let's say the decimal representation in the binary form, binary representation of the number, of a real number belonging to this interval 0, 1. So since this is surjective, this one is surjective, then that one we can conclude now that D, the cardinality of D is strictly larger than Aleph 0. That means D is not countable. So this is the same cardinality as C, that means the set of all real numbers continue. The set of all real numbers, that is not countable. But notice, so of course D is a subset of L infinity, and for any two elements, take x and y belonging to D, if x is different than y, then if you take the norm infinity between these two elements, put it like infinity, then we are always getting 1. They are always getting 1. That means the one sequence will be like a, here we have here like a one sequence, 0, 1, 1, 1, blah, blah, blah. And the other sequence is 1, 1, 1. But they must be equal, not the same. So at a certain place, for example, one will have 0, another will have 1. And then of course you see, oh, this norm will be like a supremum. And this will be x n minus yn, and of course here it will be 1, but elsewhere it can be 0 or 1, so it is equal to 1. So what did we get? We got here that there exists a sequence, not countable sequence. And now, what can I say? That if I have here a cover of this, let's say like this. Let's say consider this open set U, and look, let's say like this. For every x belonging to D, let's say I take the open set, which will be like this one, Ux, which will be the open ball of the radius 1/2 center and this x. So now suppose L infinity is, suppose for contradiction, make issue. Suppose for contradiction that L infinity has a countable dense set. Okay, call this somehow, like S1. Okay, we used S, so S1. Then, of course, this Ux is intersection and is non-empty. So that means we can associate, and there exists an element Sx belonging to the S1, which is exactly this element from this intersection. But then you see, wow, one moment, something is not correct, because if you have here x different than y, then since this Ux intersection Uy is empty, then you will get that Sx is not equal to the Sy, so we are getting again a map that is mapping D, and this is a one-to-one map into the set S1, so this is one-to-one map, and this map take phi of x is equal to Sx, and this map proves simply that S1 cannot contain uncountable subset, which means cannot contain uncountable subset, which will be of that one. It's not possible. Uncountable. So we are getting here that this set S cannot be dense and countable. So L infinity is not separable. So that's basically this statement, and let's go to the one of the let's say conclusions from our theorem, because now let me write it down, that actually we can put it like this: proposition that separability and reflexivity goes together. In our case, that means assume that E is a Banach space. Then we have that if E is separable and E is reflexive, this will be if and only if E star is separable and E star is also reflexive. So we already know that if E is reflexive, this is equivalent that E star is reflexive, so there is only question of proving the separability part. So we need to prove that in our case we already have put it like this. Proof that we already have here this way for separability comes from the theorem. So we need to, so this is from theorem, and remember E is separable, so E is reflexive if and only if E star is reflexive. So from the theorem we have that one, and in order to prove this one we just notice that E can be written as a, so assume that, let's say, assume that E is separable, then E is equal to the E double star, because it is reflexive, is separable, and again, since E star is exactly E double star, that implies, and this is by theorem again, that E star is separable. And basically, this is our first. This is the end of the lecture 5. So we'll continue separability properties next time. And thank you.